All right. I think we're going to go ahead and get started. Thanks for joining, everyone. This is the last live stream for the year. We've obviously been focusing on a lot of linear models, and the reason for that is, well, there's a few reasons. One, we've been trying to solidify sort of the overarching pipeline that can be reused from model to model, both in 1D, 2D, and 3D, and we think we've got that nailed down pretty well. Today, of course, we'll be talking about the linear Euler equations in 3D, which is our first 3D implementation using the exact same pipeline that all the other models use, which is kind of cool. The other reason is linear models provide us a framework for doing convergent studies, which we will be starting in January of next year to ensure that we're getting the correct convergence rates for the models, which basically provides us the checkbox that we've done spectral element methods correctly. So that's part of what's coming next year. I'll talk more about that here in a little bit. But let's go ahead and dive into the topic for today, which is our spectrally accurate DG solver for linear Euler equations in 3D. Both Garrett and I have been working quite hard on getting a lot of the components in place to do these kinds of things, yeah, it's been a lot of fun. So what I'm going to do is do a bit of a refresher, or if you have not been tuning into these, this should get you on the same page as everyone else here. The way SELF, the spectral element library in Fortran, sees a partial differential equation is as a generic conservation law. We have the time rate of change of some prognostic variables is going to change as a function of the divergence of a conservative flux and some non-conservative source terms. There's a lot of examples that we've already done so far. We've discussed like various ways you can pose these fluxes and the source terms for different models, but in general, like to define a specific model for your application, what you ideally need to do is provide the bare minimum is to provide pure Fortran functions that define the flux, and this is going to be both the interior flux for the elements, and since we do discontinuous Galerkin, you also need to provide a Riemann solver that's consistent with that flux, and then you provide a pure function for your source terms, or if you have none, you just don't define one. And this way you get to leverage everything underneath the hood that we've done so that you can do unstructured grids with isoparametric geometry. We've got the GPU acceleration taken care of for you for the most part, and we'll talk a little bit about that here in a bit. Yeah, from there you're basically able to get up and running. So your job to if you're looking at defining a model with SELF is to create a simple module. Usually it's 100 lines, maybe 200 lines of code to actually do, and then you're up and running with multi-GPU accelerated applications. As I mentioned, because the flux divergence we calculate in the weak form using a discontinuous Galerkin formulation. We split that flux into a surface integral where you have the normal component of the flux on the boundaries of the elements, and then you have basically an interior term that goes with that. And so far we've been doing everything in what's called conservative form, and one of the updates we have coming for you in January, it's a feature that I've been working on a separate branch on the repository, is to have what are called 2-point vectors, so that you can do split formulations of these fluxes. Now, the benefit of doing split formulations is you can actually write down entropy stable discretizations of nonlinear systems like Euler or Navier-Stokes, etc. So once the split form stuff's in, we'll start tackling our nonlinear problems. But yeah, this is where we're at. So yeah, we got a surface flux, volume flux. Now today, of course, we're talking about the linear Euler equations in 3D. I plan to have a pull request open for this to get this merged into main probably by the end of the week, this week, which is cool. Some of the use cases here, I figured I'll start highlighting some things that we're thinking about in terms of where these could be used. But generally, linear equations basically means you're just supporting sound waves and your very, very low Mach number. So take that for what it is, but there's a lot of neat things you can do. Now, ultimately, we want to do some pretty complex stuff, so where you can have background flow, where you can have changes in the background density field or temperature field, so that you have variable sound speed and background state. Today, we're looking at basically linear in a quiescent fluid. But we do have plans to add in some of those things sort of as we sort of baby step our way to the more complicated problems. Yeah. All of our documentation, as things get updated, whenever the main branch of self gets updated, you can find at self.fluidnumerics.com. They get out of the way there. All of our docs for the whatever's up on the main branch, you'll find there. So as I said, because self sees everything as a generic conservation law, let's talk about each of those components here. For linear Euler in 3D, the set of prognostic variables that we're working with here are rho, which is the fluid density, the linearized density field. It's really the perturbation off of the background state. So if you have a background density of rho naught, there's that background state there. The next three variables here are u, v, and w. So these are our three velocity components. Again, linearized off the background state, which the background state is zero flow. And then we have a pressure perturbation off that background state. Now the background pressure is rho naught c squared. So great. Now the flux term here for the linear Euler equation, much like in the 2D case, it's nothing crazy going on, but we have basically mass conservation, so really expansion and contraction of the fluid can increase or decrease the density locally. So basically we have rho naught times u vector, and then we have the pressure gradient force, which we can implement using a flux vector. So p in the x direction for that vector gives us a pressure gradient, pdx essentially for u. We can do the same thing for y and z, and we actually go ahead and forward step the pressure equation rather than just diagnosing it from an equation of state, which you certainly could do. We actually go ahead and forward step that with the whole system, which if you assume ideal gas law on the density equation, so if you use mass conservation and ideal gas law together, you can come up with an equation for the pressure here. So you end up with rho naught c squared multiplied by u vector. Initially, we're not looking at any source terms, although you could envision doing things like gravity, like buoyancy, things like that. Now, to track stability for the problem, this is an optional thing whenever you're building a model for self. It's highly recommended that you do it, but you can put in what's called an entropy function. This is a mathematical entropy function. Typically, it's a positive definite or negative definite, just any sign definite quadratic function of the state variables here. So basically what we're looking at is the kinetic energy plus the internal energy in this case, which is p over rho naught c squared. So the entropy function is that, and then basically self has some mechanics internally that can, if you define a pure Fortran function that takes in the state variables and spits out a single entropy function, we can use that to do global integration on your domain to give you a metric that helps you track stability of your solver. Now the surface flux we're using for this is, as we've been doing for all the linear problems, is a simple local Lax-Friedrichs upwind flux, which ultimately basically what you're trying to do is split the surface flux, so f dot n hat, into if you're on an edge, and I think I have a slide here in a second, but if you're on an edge, you want to look at waves that are going out of your element, waves that are going into your element, and you can diagonalize that and then use an upwinding approach to figure out which state on which side of that shared edge that you want to use. What that ultimately comes down to for linear problems is an average of the fluxes on the two sides of a shared edge plus the maximum eigenvalue, which here is the sound speed, multiplied by the jump in the solution. It's pretty typical stuff. Now, once we start going into nonlinear problems, this becomes a little bit more hairy how you do this. But once we get into flux splitting, we'll just take some very typical 2-point fluxes to implement all of this. So I'm really excited to be getting into that early next year. So I did want to talk about no normal flow because in 3D it's a little bit more challenging than doing this in 2D if you're working with spectra elements, so isoparametric elements. Now this picture here is taken from page 210 of David Kopriva's book. It's called Implementing Spectral Methods for Partial Differential Equations. And what this schematic is here up on the top here, so what's called figure 5.8 from the book, is this dark line here might be a physical boundary in your model domain, and because we use a Riemann solver, what we need to do, right, is we need to have an internal state, so this left state and this right state for to really represent what's going into the Riemann solver. So all the boundary conditions are implemented by specifying this external state. And so our job when we're defining something like no normal flow or radiation boundary conditions or prescribed boundary conditions for that matter, our job is really to define what that external state needs to be. And for what this amounts to ultimately in the Riemann solver, like I was mentioning before, when you compute the normal flux along that boundary line as a function of the left and right states, what you can do is you can write that flux function as a linear matrix multiplied by the state variables, or the vector of state variables. And then you can diagonalize that matrix. If you diagonalize that matrix, you can separate that matrix into eigenmodes that want to travel from left to right, so going this way. See if I get a laser pointer here. So if you have modes that want to travel this way across that edge, and then you have modes that want to travel that way across the edge, and then you just upwind. Now for no normal flow, because we know that the average of the fluxes ends up contributing inside of here for the actual flux calculation. What we want to do is basically set the normal component for the external state to be the negative of the normal component of the internal state. And then you have some choices to make about how you want to handle what the tangential component of the velocity needs to be. Now, when you sort all this business out for linear Euler in 2D, what you end up getting is the natural thing to do is just to say that the tangential component of the velocity field, basically that stuff that's flowing along this wall, is going to be prolonged through the external state. So you have no jump in the tangential component of the velocity, which is equivalent to doing free slip boundary conditions. So that's what we've been doing in linear Euler 2D. We did this in linear shallow water 2D. Now when you get to 3D, it's a little bit more challenging. So yeah, this is just a summary of what I just said here. So in 2D, the external normal velocity is set to be the negative of the internal normal velocity. And then the external tangential velocity component is equal to the internal tangential velocity component. So this basically gives us no normal flow with free slip boundary conditions. So if we add diffusion terms in, you can start doing some more like viscous dissipation. You can put in drag layers. Actually, there's lots of cool stuff you can do there. Now in 3D we want to do the same thing, but the hitch is that we have one normal vector, but the tangent component is actually on a plane. We have a two-dimensional surface in 3D space that we want to use. But if I take that concept of setting my external velocity in this following way, so I want to take the normal component needs to be the negative of the internal velocity normal component, and then I just want to prolong the tangential component. So basically all I'm doing is reprojecting these vectors. Rather than an x, y, z, I'll project them into a different orthonormal bases, n hat being the outward pointing normal for my geometry. And then I need to know what these two tangent vectors are that form a plane. Now, I think it was a year or so ago I had done a video on differential geometry and we talked about how to figure out how to do divergence, gradient curl, etc. in multi dimensions and in mapped coordinate systems, and we came across this definition towards the end there, known as the metric identities. And we have that on the left side. These are what are called the contravariant bases vectors. These are vectors that always point across coordinate lines. And in fact, we actually use those evaluated at the element boundaries to form the boundary normals. And because they're defined in this particular way, we actually have a nice convenient bases for the tangent plane. These AJ and AK are what are called the covariant bases vectors. They are always pointing along coordinate lines. But if I'm on a boundary and I pick a particular JAI that is the normal that is corresponding to the outward pointing normal, I know which AJ and AK correspond to that. And in fact, those guys are going to span the tangent plane. And what I want to do for basically what I get for free out of the box with this is that my normals, which are parallel to JA superscript I, my contravariant bases vectors, these are this is orthogonal both to the covariant bases vectors AJ and AK. And you can see, I mean, it's pretty straightforward to see that if I dot this equation here with AJ, the right-hand side goes to 0 because AJ cross AK is a vector that's always orthogonal to AJ and AK. All right, so you can do the same thing with AK as well. So I know that AJ and AK are both orthogonal to n hat, which is nice. But there's no guarantee for an arbitrary geometry that AJ and AK themselves are mutually orthogonal. The reason why I like orthogonality is because it makes turning this decomposition up here easy in terms of writing things back in terms of x hat, y hat, z hat components. So that's kind of why we want orthogonality. But what we can do is get t hat 1 and t hat 2 from the covariant bases vectors. So if we know AJ and AK, we can form an orthonormal basis that spans that has the same span as AJ AK, just by using a Gram-Schmidt orthogonalization of AJ AK. Nothing really crazy. I was hoping to actually have this done today, but I was chasing down a few bugs this morning. But this is actually being put in today to wrap up the linear Euler 3D basically during the geometry creation. And we used to just have a variable in the in the object that stores the metric terms and all that stuff. I think it's this SEM hex class, and it only had the n hat vector for the boundary component, so we're adding basically two more dimensions onto n hat so that we can get basically the tangent and binormal vectors, so t hat 1 and t hat 2, and those will be done just using standard Gram-Schmidt from the covariant bases vectors. So that's a little bit of differential geometry there today. I know it was kind of fast, but those are some of the new things that are coming in with the linear Euler 3D that we discovered that were needed along the way, which I think this was kind of like one of those things that you don't really think about until you try to implement these things on actual models. So it was quite nice to be able to come across this as we did stuff. I'll take a moment here just to say that if you guys do have any questions along the way here, feel free to drop them in the chat. If you find that you cannot access the chat, that's probably because you're not a subscriber. So just take a moment, subscribe to our channel, and in a few minutes that chat will be enabled for you. Okay, so this is a little bit of a refresher because I'm going to be going through some code here shortly about what's going on in the time-stepping pipeline. And I went over this a couple weeks ago when we talked about Euler 2D, so I'll briefly touch on this. So the reason I'm going to show you this is just to fill in sort of the concepts again. About how we're able to use self to do a variety of models. But because it's object-oriented Fortran, at any point when you're building your own model, if you wanted to override any of these things to customize these pipelines, you can absolutely do that. But for the most part, these things work out of the box for you. So at the bottom end of all of the like models implemented in class is an abstract class called the self model. That abstract class does have some concretized methods, but those concretized methods call abstract things. So we have what's called the forward step method. This is baked in for all of our explicit time stepping schemes, but it basically takes in a final time you want to get to, how frequently you want to dump file I/O and report, like entropy and things like that, and then basically steps through doing that. So right now it's all fixed delta t, so fixed time step size at the moment. But that's basically it. So basically we call a time integrator. This could be your Euler, your RK3, Adams, Bashforth, etc. We write the model, increment an I/O counter for file I/O purposes, and then we calculate entropy and report any metrics that you're interested in. Okay. Now the time integrator, like I said, it could be any of these methods. We've provided a number of these out of the box. I call these abstract-ish methods in the sense that they themselves do call abstract methods from the perspective of the self-model class. So we have calculate tendency, update solution. Those actually start to get concretized in the DG model 1D, 2D, and 3D classes. Okay. Each of those classes, the DG model, 1D, 2D, and 3D classes, are type extensions of self-model, and they start to concretize things, but they only go so far, basically to get you to a point where you can just define pure Fortran functions to concretize your model. Now, the way that the tendency calculation works, so basically if you're trying to forward step a PDE, what you need to do is for each prognostic variable and for each point in your grid cell, you need to tell me what the time rate of change of the solution is. And we do this using the formalism of divergence of a flux plus a source term. Now there's things we do for you in advance. So coming in, we have the solution at all the quadrature points. What we do is prolong that solution to the boundaries. So you now know the solution at the element boundaries, and then we do the side exchange. This is where all the magic happens with MPI, and if you're not using MPI, even if you're exchanging data between elements on the same process, there are buffers that need to get filled to make that happen. So that's done there. This is a generic routine that we found useful in experimenting with other nonlinear models, where you can start to do more complex stuff, like if you want to calculate primitive variables from conservative variables. Like for example, in nonlinear Euler, what you really track are momentum, density, and internal energy, but you might want to actually calculate temperature or velocity, or pressure or enthalpy, etc. Those kinds of things can be done by overriding this pre-tendency scheme, but it allows you basically to take advantage of the fact that you know the solution both at the interior points as well as at the boundary points. Then you can actually set the physical boundary conditions. So on physical boundaries, so things that are edges in the domain that do not have a shared neighbor are classified as physical boundaries, and they usually are accompanied by a boundary condition ID flag that we actually read in from various mesh files. So yeah, you can set boundary conditions. Now we have some baked in ones like no normal flow, radiation, prescribed. And we actually are working on a feature to where you can just add your own whatever boundary condition flag you want. But that's where that's done. If you have gradients enabled, basically what we'll do is go through and do what's called a Bassey-Rebay method. So the solution gets averaged at the sides, and then we use a DG form of the a weak form of the gradient operator. And for the boundary fluxes for the gradient, we use the average of the solution variables at those sides, and then we can set the gradient boundary conditions. So, as I mentioned before, what we had talked about in the last couple slides was doing hyperbolic fluxes. So these would be like your parabolic fluxes for your diffusion terms. You can also, just like you can do boundary conditions for no normal flow, prescribed, etc., you can do that as well for your gradient boundary conditions. And then we average the gradient on those sides, because ultimately to construct diffusive flux, we'll then take the average value of the gradients as part of the Riemann solver for the diffusive flux. Then you get your source method, boundary fluxes, and then the actual flux method, which is going to calculate the interior version of your flux. So this is that surface flux for all your elements. These are the interior fluxes at all the quadrature points, and then we combine all that to create a divergence, and then we add them up. So you do a source plus a divergence. That's the generic pipeline. If you don't like the pipeline, again, it's 004 you can override that calculate tendency method in any of your specific models. But for most cases we've been playing with so far, this actually works quite well. You don't really need to change that. So here's an example for a volume flux. I think this is, actually this is how the volume flux works under the hood. So one level down here, we have on the CPU side a do concurrent loop. We have ds dx is taken from the solution and solution gradient fields, and then we use this pure function. It's actually a type-bound procedure. It's a pure function there that you override to do your flux definition. Okay. Now, when we do GPUs, the GPU versions of the code, automatically we've added hit memcopy or CUDA memcopy, depending on which GPU you're working on. Now, what this means is that although you can get the correct answer, out of the box, if you do GPU acceleration with a model without defining the kernel specifically to do like these do loops, it might not be the most performant. And I'll show you an example of that when we look at code here in a minute. Just so I think I tried doing it last time and I just didn't quite get have enough time, whatever. So, anyways, we'll look at it again if I did it already. I can't even remember anymore. All right, so before we look at code, this is my plea for help. We basically spend a lot of our free time working on this. We do have two fantastic collaborators who have been grateful in sponsoring us, and we would love to have more of you join. There's a lot of ways you can support us. Of course, subscribing to us on YouTube helps us get closer to the goal of being able to monetize everything we're doing here, which would motivate us to keep doing this kind of stuff. You can use Self for your projects. Give us a star on GitHub, and if you need help, open issues and ask us questions. All of those things mean a lot to us, just to know that you're even taking some time to use what we're building. If you can go further than that, you can support our project on Open Collective. We are our own fiscal hosts there. All your proceeds go directly towards paying time and labor as well as compute expenses to do all the development and testing. And you can work with us. If you are a researcher, if you're at a government lab, at an educational facility, or at any commercial organization, we do GPU acceleration work all the time. For a lot of people, we do a lot of work on Google Cloud for high-performance computing. We've got a lot of skills that I think translate, and work with us. That's the only other way. All right, let's take a look at some code. All right. So the linear Euler 3D, what we're going to look at first here is just, since we already talked about the pipeline and everything, I just want to show you briefly how all this is set up for linear Euler 3D. Again, just to give you another example, if you're thinking about implementing your own model, how you could do this. So what we've done so far is we've basically done, so if we're doing a 3D model, we're basically doing a type extension of the DG model 3D class. And we're going to call it here linear Euler 3DT. Now, the reason why I use this subscript T is because we do support multiple backends. So underneath the source directory, there are additional directories, CPU and GPU. Those provide specific concretizations for the particular backends. You'll notice this APU is up here, and that's actually because we just got in-house our MI300A system. Thanks to Supermicro and AMD for making that happen. And we're getting that moved into a co-located facility at the beginning of January nearby, which is it's quite exciting. But it's a different architecture. I mean, it's kind of like a GPU, but you have a shared memory space between CPU and GPU cores. So there's some nuances there on how we're going to do memory management. But at any rate, we have these base classes directly underneath the source directory. All of them have this subscript T on them, and then they get fully concretized through type extension higher up. So like in the CPU, if I look at linear Euler 3D, you can see that linear Euler 3D is actually a type extension of this, and it does nothing special, right? It doesn't do anything different. The reason why is on the CPU, all the CPU instructions are actually provided here. But what this allows us to do is conditionally compile depending on the target architecture you're doing. So for us, this makes it a lot more maintainable to write code that works on multiple platforms. So at any rate, let's look back at linear Euler 3D. So we've added a few attributes. Rho naught, a reference density, reference sound speed. Both these are constant right now. And then gravitational acceleration, which we're not using gravity yet, but we do have plans to get that in there. Now the methods that we've overridden are source. There's the set number of variables. I didn't mention this guy, but it seems to be the cleanest way to allow models to enforce models to have a specific number of variables without, basically making people be aware of all the data structure components. So yeah, we'll use that there. You can set the metadata. It's not required, but it does make your HDF5 files nice because it'll actually apply names that are meaningful to you, to your output, which is kind of cool. We got our entropy function, flux 3D, Riemann flux 3D, and then source we're actually not going to do. I'm going to go ahead and remove that guy. But we did override source method because if we're not defining a source, you can actually save some compute cycles if you just make that guy return and do nothing, so it just gets optimized out by the compiler. Set number of variables, so this guy for 3D Euler, we've got density, U, V, W, and pressure, so that's 5 variables. Great, that's all we're doing there. And then for the metadata, we have for each component of the model class, you can go through and name, provide a name for the variables as well as set the units and a description. So here I'm just doing name and units, so we're doing rho, U, V, W, and P. And you can set the units however you like. Okay. The entropy function, as I said, we have a sum of the kinetic energy. So it's 1/2 U squared plus V squared plus W squared. So this is kinetic energy per unit mass. And then we have the internal energy per unit mass as well. Yeah, so like I said, we override the source method to basically return so that it gets optimized out because there is no source term. We don't want to just waste compute cycles on doing a deep 5-nested loop to specify source terms that are basically 0. So this is a quick hack we figured out to save some compute cycles and speeds up both the CPU and GPU components of the code. It's quite nice. For the 3D flux, basically, like I said, these are all pure functions. So what they take in as input is the state variable, the state gradients, and then it returns a flux, which is indexed by the variable dimension first, so which prognostic variable you're computing the flux for, and then the physical space direction. So we got flux for density, x velocity, y velocity, z velocity, and then the pressure. And then the Riemann solver, again, it's doing exactly what I said before. It's doing local Lex-Friedrichs upwind method. And then we did provide a convenience thing. Oh, that should be Z. Let's fix that. We're starting to build into a lot of our classes some simple stuff to do, and common initial conditions, so that you can kind of stitch things together much easier. Which that is the other nice thing about what I think is the nice thing about what we're doing here is, like, even if you don't want to build a model from scratch yourself, these models that we're providing should provide you a basis to do more complex things, especially once we get into the nonlinear models. Being able just to use those as pre-canned model classes out of the box would just be really nice. But yeah, this one, all it does is it just makes a Gaussian disturbance, a disturbance in the shape of a 3D Gaussian function in the density and the pressure with 0 velocity field. So you basically have a high pressure zone, and it wants to evacuate air out of that high pressure zone. So that's all that is. Pretty straightforward. Now the GPU implementation, to get this fully GPU resident, and this was that bit I'm going to talk about here about performance differences. So like if you did this, just this, and you had your CPU and GPU subdirectory type extensions basically doing what I have, let's see here. So this on the right side is the CPU type extension. Basically, if you put this in both the CPU and GPU subdirectories, it will work. You will get the right answer on both the CPU and GPU platforms, but the performance on the GPU side is not going to be as good as it could be, and I'll explain why here in a minute. So what I wanted to do was actually show you an example of what's going on here. So I've actually pre-built a number of a few flavors of the code. So down here in the terminal, which I'll expand this up. All right, so I've got this build, I've got CPU build, and then I've got GPU non-resident build. Okay, so the build is a GPU build targeting our MI210 GPUs, which I don't know why they're not showing up there. Maybe I have the wrong version of ROCm loaded. Okay, well, they're MI210s. Let's see, ROCm info. You gonna tell me the right thing? There we go, AMD Instinct MI210. So yeah, we have in the build directory, we're targeting the MI210 GPUs. CPU build is just doing a multi-core build, so it's basically all the do concurrent loops get multi-threaded with OpenMP when we use the GNU compilers, and we're using 8 threads to do that. And then we have the GPU non-resident build. So I just want to first give you a flavor of how different the performance is between them just from running it at the command line. So in our examples, there's a number of examples that get pre-built when you install Self. So we'll do linear Euler 3D spherical sound wave with radiation boundary conditions. So radiation boundary conditions is quite easy. You just set the external state for the linear models to 0. You want to inject no perturbations back into your system, so that's quite nice. So it'll take a few seconds here. Now we have instrumented timers, so we'll get a number here, and I'm going to jot this down. Okay. I'm going to pull that off to the side here. So the time to complete, so we're just doing 200 time steps here. So let's call that 15.98 seconds. And that's on 8 threads, with 1 thread per core on our system. Okay, so that's that. Great. Let's take a look at our. So if you were to just provide the pure Fortran functions and then not do any explicit kernel writing to make the code fully GPU resident, let's see what we get here. That's what this is. So this is basically implementing only the stuff in the self linear Euler 3DT class and then doing just an opaque extension in the CPU and GPU classes. So we haven't explicitly written kernels to replace the actual flux evaluation, source term evaluation, etc. So let's do linear Euler 3D. Okay. So we got 15.98 for seconds for 200 time steps with CPU only. Okay, and now we're at 10.42. So that's let's see, 10.42. It's faster, right? But it's not as fast as I like it. It's only 1.5x faster than the CPU only multi-threaded version. Now, before I show you the next result, I need to say that our CPU only implementations are actually not too great. They're not terribly optimized, and we actually have an open issue to look into this. I've got a few things in our self mini apps repository I may have mentioned a bit ago, where we're looking at different ways to do basically flux divergence is the big hog killer, but there's a lot of optimizations that we're looking at, and we're getting some promising results here. So keep that in mind when I do this next. When I ran it earlier, I was like, there's no way that it's that fast, but yeah, it is. On the GPU, we have done an extensive amount of work to optimize all of our kernels. Like, we spent most of our time there, and it definitely shows. So if I run here, linear Euler 3D spherical sound wave, so same problem. I mean, that came back almost immediately, and you can see for 200 time steps is 1.353 seconds. Hang on here, I'm getting a battery alert on this thing. All right, I think we're good. And let's get that sorted. There we go. Okay. All right, so this run we're like 10 to the minus 2 seconds, so that's significantly faster. So let's pull that back up. So that's 0.0135 So let's just call it that. So yeah, about 1,000 times faster on the GPU. But again, it doesn't mean that GPUs are great for everything. What it means to me is, our GPU kernels are fairly well optimized. And in a couple live streams ago, I had actually talked about how we did this, how we got our kernels so fast, basically using shared memory to preload fixed size blocks of our data. And to get rid of L2 cache misses, as well as basically using what are called launch bounds to optimize the register allocation. So yeah, our GPU kernels are quite damn good. Our CPU kernels need a bit of work. So this ratio and performance difference is not reflective of the ratio of the CPU performance capabilities, the GPU performance capabilities. It's more of a reflection of how poor our CPU kernels are at the moment. So now the one thing I want to call out here is so the first GPU run I showed you took 10 seconds roughly to do all those computations with the claim that, oh yeah, it's running on the GPU, and it is, but it's not what we call fully resident. Now when we make it fully resident, you can see that's where a lot of the gains come from. So if I were to take that 10.42 right, and divide by 0.0135, right, that's 771 times faster, basically making it fully GPU resident. And the reason why this occurs is there's a lot of data that goes in flight between the host and device if you do not make that code GPU resident. Now, this is my little hint about what's coming with the APU, because the APU, the MI300A, actually shares HBM memory between the CPU and GPU cores. We do not have to pay those mem copy costs. So on an APU platform, you could actually get away, I think, with just doing this for your GPU offloading and let us run everything else on the GPU. But what will happen is the CPU counterpart will just run on the CPU. That's fine. There's nothing wrong with that. And in fact, since we multi-thread it, it actually probably do pretty darn good. And because the CPU and GPU spaces are shared, we don't have to pay that mem copy cost. So I think when we run this on the APU, we should see fairly close, much closer performance. So the ratio of these two runs should come down quite a bit on the MI300A, which means less coding for better performance, which we like. It's quite nice for that particular architecture. So stay tuned. In the early parts of next year, we'll be basically rerunning a lot of these on the MI300A once we get them ported. So that'll be fun. What I did want to show you, though, is a trace profile. Now, this is the part I can't remember if I showed you or not. So what I'm going to do is actually pull up a separate one here. So we use rockprof with the systrace flag to get the profiles out. In fact, let me just go ahead and show you how that's done. So I'm going to, this is my fully GPU resident build. So we'll do rockprof systrace linear Euler 3D. Basically what that's going to do is it's going to profile the code, and it's going to spit out a JSON file that gives us a timeline of events that occur on the GPU, and then we can open those with Perfetto, which is this website I went to, ui.perfetto.dev. We'll open that trace file. The results, the non-resident results are the ones I really want to show you here. So this is the one where we just do the pure Fortran functions. Uh-oh. Yeah, we got an import error. That's a big file. That might be why. Sometimes Perfetto is finicky with larger files. Let me run that one again, and I'll download that. And what I'll do is non-resident build. Let's do that rockprof again. Okay, we're going to do it here on the non-resident one. We're going to download this file again. Oops. So I'll let that run. And then we'll get that visualized, hopefully. Okay. download. I'm going to overwrite that guy. Okay, so that is still downloading. Give that a sec. While that's downloading, let's go ahead and look at the trace profile for the other. So this is our fully GPU resident setup, and there's 3 phases to a GPU resident code primarily, at least in the context of like PDE solvers. You have this initial step where there's usually like some allocations going on. You're setting up your memory space that you're going to work with. You're reading in stuff from files, probably, like if you're doing, reading in mesh files, initial conditions, etc. All that's happening here. So there's a lot of what we call overhead. You're doing loading things onto the CPU and then copying the data over to the GPU primarily. And then you get into this other phase where you're actually forward stepping. And when you forward step the code, really the only time you need to get data off, or you should only have to get data off, is when you want to write data to file. Okay, so what you see here going on is a whole bunch of kernels stacked back to back, right? And that's basically reflective of our actual pipeline for the code. So if I were to go back up here, so here's the start of a pipeline. So we have boundary interp, so we're prolonging this data to the boundaries. There is a little bit of overhead basically in between these guys. That's really from ROCm. So any optimizations on ROCm and the AMD GPU drivers are going to fix these kinds of gaps. And we have side exchange. Oh yeah, there's some other things like hip graph that we could probably use to squeeze those out of there, but that's another story. Yeah, side exchange, set our boundary conditions, boundary flux methods. This is basically our pipeline, right? But everything's running back to back. Every single time, there's no data copies happening in between, right? So if I were to look, so here's when I write my initial condition. I copy from device to host, and then I write out the final state of the solution. So again, another copy device to host, but there's nothing in between. I'm not copying data back and forth. So all I'm doing is computing. It's nice, it's tight, it's fast. Let me refresh this, and in fact, let me just get a new UI. Yeah, let's see if I can get this guy to work. Fingers crossed. Yeah, it's still giving me data loss. Well, let's see. What's going on in here is, so this row here shows all the data copies that are happening. And then this row here shows the actual GPU activity. So again, we still have our same kernels inside of here, right? But now between each of these kernels, we have these mem copies that are happening. And while just doing the pure Fortran functions is nice to get the model in and get it correct, because in between we actually have to run host side kernels to fill in those things from the pure functions that a programmer provides us. It spreads out all these kernels. So you have data going back and forth across host and device. You're running stuff on the CPU, you're running stuff on the GPU. Now, there are opportunities to overlap CPU and GPU computations. These are things we are exploring to improve this in the event that someone doesn't really want to write GPU kernels. But these are the limitations you're up against. Of course, the other route is to do what we did for the GPU resident code. Let me put these back in, is where you actually override some of those methods from the self DG model 2D or DG model 3D class, where you redefine boundary flux and flux method, for example, and the set boundary condition. And essentially what we do is you will write, so here's a it's HIP code. Basically it's CUDA kernels or HIP kernels with a wrapper function that actually executes all those things on the GPU. So yes, you have to write some C++ to make this happen. And then you use mixed language programming to bind stuff from your C++ files into Fortran. You basically make it look like a subroutine to Fortran, and then you just call those inside of there. So you're basically offloading the rest of that code to the GPU, but for 700 times in performance improvement, it's not bad. Now, this is one of the support things that we want to be able to do for you. So it's like if you can get to the point where you have defined a model and it has those pure Fortran functions, we're smart enough to be able to translate all that to the GPUs using the data layout structures that we know are inside of Self. Ultimately, it'd be nice to be able to automate that, but we're at where we're at at the moment. So I hope that you found this informative, useful, fun, a glimpse maybe into how you might be able to use object-oriented Fortran for your projects. Of course, if you are interested in using Self for your projects, we want to help you. You can always reach out to us at support at fluidnumerics.com. You can open up issues on the GitHub issue tracker, which reminds me, let me go ahead and open that up. So if you go to GitHub under Self, on our issue tracker, we have a number of things that we're looking at. Right now, the big one we're trying to just get through at this point is finish off this checklist for our first official release, which will be coming soon. This is where we're at. We're finishing up linear compressible Euler 3D. And then we've got some miscellaneous things that we need to clean up in the code, and then we're going to go ahead and tag a release. Once we tag a release, Garrett and I are working pretty hard to put together deb, RPM, tarballs, Docker images, etc., to make those available for you guys just to start using Self out of the box. All of these will provide builds for a variety of supported GPU targets, CPU platforms, etc. So we'll have some documentation to follow up with in January on that. So yeah, once we have the tag release, we will go ahead and start putting these packages together, and then we'll retroactively put those in. Those what do you call them? Artifacts into our releases. We'll also be putting a Self package into SPAC, so you can just SPAC install Self with all the variants that we have, so double or single precision, AMD GPU, NVIDIA GPU. That will make that much easier. And that will round that out. We have a number of other things that we're looking at. Again, we had actually one of our collaborators is interested in a sediment transport model. So we're looking at that. We are looking at split form methods for entropy stable, entropy conservative schemes. And to do that, we basically need to revive some old stuff I had to do 2-point vectors. So we'll be getting those in very soon, and then we'll start our nonlinear modeling. I've gotten requests from other folks that we've been talking to, just sort of offline, to do a broader range of mesh file support. So one, we are going to put in HokeMesh mesh reader for both 2D and 3D HokeMesh files. And then we're also going to put in support for Abacus files as well. So if you're using things like Coreform Qubit, or if you've already got codes, meshes that work with Abacus, those will be able to work with Self. Yeah, so there's a few things on our short-term list, but we want to hear from you, the potential user, the current user, whatever you are. If you do have any questions, I'm going to hang here and have some tea for a moment. You can drop your questions in the chat. But yeah, that's what we got going on. All right. Thank you, Nicola. It's good to see you again, man. Yeah, I'll be around. Again, you can hit us up on the GitHub issues. You can email me at support@fluidnumerics.com. A number of you know where to find me on LinkedIn. I always respond to people there. Yeah. If there's nothing else, guys, I wish you all a very happy holiday, restful break. Take it easy, and I will see you next year.